Welcome to the deep dive. Today, we're taking a look into the world of supercapacitors. These are kind of the unsung heroes of energy storage, you know?
That's a great way to put it. They're these incredibly powerful devices, quietly bridging a really crucial gap in our technology landscape.
So our mission today is to really unpack them. What are supercapacitors? Where are we already seeing them pop up?
Right. And crucially, what's holding them back from being everywhere?
Hmm?
Because they have amazing potential.
Hmm.
And this is the really exciting part. We're going to dive into some brand new research, like hot off the press.
Research that could potentially sweep away a lot of those limitations we mentioned.
Exactly. We're talking about innovative carbon electrode materials. Stuff that could honestly revolutionize everything from the gadgets you carry around every day to like the stability of entire power grids.
Okay, sounds fascinating.
Hmm.
And for this deep dive, we're drawing on the big picture from Wikipedia's supercapacitors article and also getting specific with a very recent patent application. That's US 202500511167A1, right?
That's the one. It details a carbon electrode material for improving the performance of supercapacitors and method of making carbon electrode material. So let's get into it.
Right, so maybe start with the basics. What exactly is a supercapacitor? I've heard ultracapacitor too.
Yeah, they're often used interchangeably.
Yeah.
So picture a spectrum for energy storage. On one side, you have your standard capacitors. They're incredibly fast, like lightning fast, but hold almost no energy.
Okay.
On the other extreme, rechargeable batteries. Lots of energy storage, right?
Yeah.
But they charge and discharge relatively slowly, and their lifespan, well, it's limited, maybe hundreds, perhaps a few thousand cycles if you're lucky.
So supercapacitors must sit somewhere in the middle then.
Exactly. They are that bridge. They hold much, much more energy than a conventional capacitor. Think 10 to 100 times more per unit of mass or volume. That's a huge difference.
Wow.
But, and this is key, they can still charge and discharge way faster than batteries. And the cycle life, it's staggering. We're talking potentially over 1 million charge and discharge cycles.
1 million. Seriously. That's almost hard to grasp compared to my phone battery that feels like it degrades after a year or two. How do they manage that? How do they store energy without that solid dielectric thingy that normal capacitors have?
Right, no traditional solid dielectric.
No.
It's actually quite clever. They use mainly two mechanisms. First, there's electrostatic double-layer capacitance, or EDLC. Think of an incredibly thin layer. They call it a Helmholtz double layer, forming right where the electrode surface, usually carbon, meets an electrolyte solution.
Okay.
Charges line up across this layer, separated by just a tiny distance, like a few angstroms. We're talking tenths of a nanometer.
Yeah.
It's all about maximizing the surface area for these charges to gather.
So it's more of a physical charge separation, not really a chemical reaction like in a battery?
Precisely for EDLCs.
Yeah.
But there's a second mechanism often involved, electrochemical pseudocapacitance. Now, this does involve very fast, reversible chemical reactions, specifically electron charge transfer or Faradaic reactions.
What?
But these happen just on the surface of special electrode materials, like certain metal oxides or conductive polymers. Unlike battery reactions that go deep into the material, these surface reactions are super quick and don't degrade the material nearly as much.
Gotcha. So it's a mix of physical charge storage and these fast surface reactions.
Right, and the balance depends on the specific design. A key difference from batteries, though, is how they release energy. Supercapacitors store energy linearly with voltage, so their voltage drops smoothly as they discharge, providing very consistent power. Batteries, tend to hold a steady voltage and then just fall off a cliff.
That linear discharge sounds really useful for certain applications. Which leads me to ask, where are we actually using these things today? They sound pretty advanced.
Oh, they're more common than you might think. In consumer electronics, think about the flash and digital cameras. Some use supercaps to charge that flash in like 90 seconds.
No more waiting ages for the flash to recharge.
Exactly. They're used to stabilize power in laptops, PDAs, GPS units, smoothing things out. There's even a cordless electric screwdriver that uses them. Charges in 90 seconds, holds 85% of that charge for 3 months. Pretty neat, huh?
That is neat. I could definitely use that.
And then you look at power grids in industry. They're crucial for buffering fluctuating power, especially from things like EV chargers, which can really hammer the grid. They provide backup power for RAM, microcontrollers, keep things alive during brief outages. They're in UPS systems.
Uninterruptible power supplies, right?
Yep. They even help adjust wind turbine blades if the main power cuts out, or manage energy flow in microgrids. Really versatile.
And I heard they're even used in medicine.
Absolute critical there. In
Wow.
medical defibrillators, they deliver that massive jolt of energy, maybe 500 joules needed to shock a heart back into rhythm. That rapid, high-power burst. Perfect for a supercapacitor.
Wow.
The military uses them too. Their low internal resistance is great for starting huge engines quickly, like in tanks or submarines, and for providing high current pulses for things like radar or laser systems.
But I feel like the biggest impact, or at least the most talked about, is in transportation, right? Especially regenerative braking.
Oh, absolutely. That's a huge area. Capturing energy when braking in cars, buses, trains, even cranes and elevators, and storing it in supercapacitors for later use. It makes a massive difference in efficiency.
Can you give an example?
Sure. Look at light rail. In cities like Mannheim or Paris, some trams use supercapacitors. Allows them to run without those overhead power lines for stretches, saving maybe up to 30% energy because they recapture braking energy so well.
That's significant.
It really is. Or think of Shanghai's Capabuses. These buses recharge at stops in just 30 seconds. And that quick charge lets them run for about 4 kilometers.
30 seconds for 4 kilometers, that's amazing.
Isn't it? And in motor racing, you see them in Formula One's KERS kinetic energy recovery systems. Toyota's Le Mans hybrids use them. IndyCar brought them in for 2024. They provide those quick bursts of power for acceleration.
Right, for getting out of corners fast.
Exactly. And even in regular hybrid electric vehicles, like Mazda's IA-Loop system in the Mazda 6, it uses supercaps for regenerative braking, and they reckon it cuts fuel use by about 10%. Peugeot Citroën uses them for quicker stop-start systems too.
Okay, so they're clearly very useful, very powerful in specific ways. But if they're so great, why aren't they just everywhere? Why aren't they replacing batteries wholesale? What are the hurdles?
Yeah, that's the core question, isn't it? The biggest limitation, generally speaking, is still energy density. While they're fantastic at delivering power quickly, they just can't store as much total energy as a battery the same size or weight for long-term use.
So great for sprints, not so much for marathons.
That's a perfect analogy. You wouldn't power an electric car for hundreds of miles solely on supercapacitors, not yet anyway. They're brilliant for bursts, for quick charge-discharge cycles, but not for storing large amounts of energy for extended periods.
Makes sense. What else?
Another major challenge is the electrode material itself. It's this tricky balancing act. You need incredibly high porosity, basically, lots of tiny holes in surface area for the charges to accumulate.
Right, for the EDLC part especially.
Exactly. But you also need high material density, so you can pack enough material into a practical small device, getting both high porosity and high density at the same time. That's really, really difficult. They often work against each other.
And I remember you mentioning graphene earlier. That seems like a miracle material, but it has issues here too.
It does. Graphene is amazing on paper, but when you try to make electrodes out of it, the individual 2D sheets have this really strong tendency to, well, to clump back together. They restack.
Ah, like stacking sheets of paper.
Kind of, yeah. And when they restack, you lose a massive amount of that usable surface area. Plus, it makes it harder for the ions in the electrolyte to move quickly through the material, so performance tanks.
So graphene's potential gets bottlenecked by this restacking problem?
Precisely. And then there's always the challenge of making these advanced materials cost-effectively and sustainably, especially dealing with the chemicals, the catalysts, the high temperatures often involved.
Okay, so energy density, the porosity versus density puzzle, graphene restacking, and manufacturing costs, quite a few roadblocks.
Definitely. But that's exactly where this new research comes in. It's like they took aim directly at these challenges.
Right. This patent application, US 202500511167A1, the team from the U.S. Department of Energy, including the lead researcher, Dr. Viet Hung Pham, along with Christopher Matranga, Kongjun Wang, Jennifer Weidman, and Yuan Gao. What did they manage to do?
They developed a new type of carbon electrode material, a CEM, that seems to crack that porosity versus density problem. It maintains really high porosity and high material density, and critically, it solves the graphene restacking issue.
Okay, how? What's special about this material Viet Hung Pham and his colleagues created?
The structure is the key. They describe it as a hierarchical, interconnected 3D network. Imagine thin sheets of graphene, but they're all crumpled up and interconnected, forming this sort of porous 3D sponge.
Crumpled graphene.
Yeah, it ranges from just one layer thick up to maybe 20 layers in different spots. This crumpled 3D architecture physically prevents the sheets from stacking flat against each other.
Ah, so the crumpling keeps the surface area accessible.
Exactly. It preserves graphene's amazing electrical properties and creates these pathways for ions to move through really efficiently. No more traffic jams for the ions.
Clever. What else stands out about this material?
It has this really interesting mix of pore sizes, micro, meso, and macro pores, ranging from microns down to less than a nanometer. This helps with accessing all that surface area quickly. And speaking of surface area, it's huge.
Oh, huge.
The specific surface area measured by the BT method is between 1,400 and 2,200 square meters per gram. One specific sample they made called 3DG900 hit 2,113 millimeter gene.
Wow, 2113. How does that compare?
That's apparently the highest ever reported for these kinds of 3D graphene materials. It's over 24% higher than a common commercial benchmark material. That translates directly to more potential energy storage.
Okay, massive surface area. What about quality? Purity, conductivity?
Very high purity. They report a much better carbon-to-oxygen ratio than typical materials, meaning fewer oxygen-related defects. And it's highly crystalline, with few defects in the graphene structure itself. This shows up in Raman spectroscopy measurements they report.
And conductivity, do they need to add anything extra?
That's another neat part. The conductivity is excellent, typically 1,000 to 2,500 Siemens per meter, sometimes higher. And Christopher Matranga and the team point out this is achieved without adding extra conductive fillers, like carbon black, which is often needed.
Which simplifies making the electrode, right? Fewer materials, simpler process.
Definitely simpler, likely cheaper too.
So how did Kanjun Wang, Jennifer Weidman, and the rest of the team actually make this stuff? Is the process practical, scalable, sustainable?
That's another area where they innovated quite a bit. Instead of starting with solid carbon, which can be tricky to process, they used inexpensive, abundant liquid or semi-liquid feedstocks. Things like coal tar pitch, petroleum pitch, even potentially bio-oils or melted plastics.
Using liquids, does that make mixing easier?
Much easier. They mix this feedstock with a catalyst potassium carbonate, K2CO3, using a high ratio of feedstock to catalyst. This ensures really intimate contact. Then they basically melt the feedstock so it coats the catalyst particles, heat it to carbonize it into that 3D nanosheet network, and then use higher temperatures like 900 to 1100 degrees C to convert those nanosheets into the final crumpled graphene structure.
Okay. Sounds complex, but potentially scalable if you start with cheap liquids. But you mentioned sustainability. What's the breakthrough there?
This is where Yuan Gao and the team reported something really cool. After they make the material and wash it, they collect the wash water. And they figured out how to recover and regenerate the potassium carbonate catalyst from that water.
They can reuse the catalyst.
Yes. And they state it's the first documented report of successfully recycling K2CO3 used this way for graphene synthesis. They achieved 95% recovery over 10 cycles, and the recycled catalyst still produced high-quality 3D graphene.
That's huge for cost and environmental impact. Reusing the catalyst makes the whole thing much greener and potentially way cheaper at scale.
Absolutely. It tackles one of those major roadblocks we talk about head on.
Okay, the material sounds amazing. The process sounds innovative and sustainable. But how does it actually perform in a supercapacitor? What are the numbers?
The performance metrics are really impressive, especially because they tested it under conditions relevant to real devices, specifically high electrode mass loadings.
What does high mass loading mean practically?
It means packing more active material onto the electrode surface, like 30 milligrams per square centimeter in some tests. That's about 3 times higher than typical commercial requirements. Achieving good performance here is critical for making devices powerful and compact.
Gotcha. So how did it do at these high loadings? Capacitance.
Exceptional capacitance. The gravimetric specific capacitance, that's farads per gram of material, hit 182.6 farad gas at a current density of 1.0 age, even at that high 30 milligaussimeter loading. That's roughly 50% higher than the commercial benchmark material, Kurai YP50F.
50% higher is a massive leap. What about areal capacitance? That relates to device size, right?
Exactly. Areal capacitance tells you how much energy you can store per unit area of the electrode. They achieved an ultra-high 5.48 farads per square centimeter, FCM at 1.0 AG.
5.48 FCM MSE, is that good?
It's fantastic. The patent notes it's more than 3 times higher than typical commercial needs, and the second best value reported for any carbon material at these demanding high mass loadings. It means you could potentially shrink devices significantly while maintaining or even boosting performance.
Wow. Okay, so capacitance is great. What about energy and power density, that sprint versus marathon thing?
Good energy density for a supercapacitor, around 10 watt-hours per kilogram, (lbh/kg), using standard aqueous electrolytes, which is consistently higher than what others have reported for high-mass loading carbon supercaps. The patent suggests potential for 8 to 20 Wh kilograms, depending on conditions.
Still lower than batteries, but high for a supercap.
Right. And the power density is excellent. They demonstrated good energy density even at very high power delivery, like 4.5 Wh kilogram at 46 to 50 watts per kilogram. Perfect for those quick bursts of power needed in EVs or grid applications.
And durability. Did they maintain that million cycle potential?
They showed superior cycling stability. It kept about 80% of its capacitance after 20,000 cycles, even operating at a slightly higher voltage, 1.2 V, than standard aqueous systems. That's really promising for long life.
20,000 cycles with good retention is definitely solid.
And importantly, the internal resistance, the ESR, was very low. This means it's very efficient, less energy wasted as heat, more power delivered quickly.
So, pulling it all together, why do these results from Viet Hung Pham and the team really matter? What's the big picture takeaway?
The big takeaway is achieving this combination of high capacitance, good energy power density, and excellent stability, specifically at those high mass loadings needed for real products. It bridges the gap between amazing lab results on tiny amounts of material and something you can actually build a practical, powerful device with.
Because the performance doesn't just disappear when you try to scale it up into a real electrode.
Exactly. The weight of the other stuff in the device, the collectors, the separator, the packaging, doesn't dilute the great properties of the active material nearly as much because you can pack so much high-performing material in.
Yeah.
It makes a translation from lab-scale wonder material to actual technology much more direct.
What an incredible journey we've taken today. From understanding the basics of supercapacitors and where they shine, to seeing the challenges, and now exploring this genuinely exciting breakthrough from Viet Hung Pham and his colleagues. This 3D graphene, especially with its sustainable and potentially low-cost production, feels really significant.
It really does. It offers this potent mix,
Yeah.
top-tier performance, expected long life, and a manufacturing process designed with cost and sustainability in mind from the start. That's a powerful combination.
You start imagining the possibilities, don't you? Like your phone charging in literally seconds. Electric cars getting maybe not battery level range, but perhaps much faster charging or better acceleration and regenerative braking. Renewable energy grids becoming way more stable and efficient.
Absolutely. Innovations like this, especially the recyclable catalyst part, making large-scale production more feasible, they genuinely pull that kind of future much, much closer. It feels less like science fiction.
Definitely. So here's a final thought to leave everyone with. If this technology for making these high-performance, high-mass loading graphene electrodes really takes off and becomes industrialized, what else could we do with it? Beyond energy storage, where might this incredibly versatile, highly conductive, high surface area material show up? How could it reshape industries we haven't even thought of yet?
That's a great question. Maybe catalysis, filtration, advanced composites. The possibilities with high-quality, affordable graphene are potentially vast.
Something to definitely ponder. Thanks for joining us on this deep dive.